Okay. So yes, so for this first one, we're drawing the IUPAC names for both of these. So we go ahead and start by numbering the cycloalkane. So 1, 2, 3, 4, 5, 6. I did this one as 1 just because it has 2 groups on it, so I would think it would be more higher priority. And then this one has 1, so we went around this way. So yeah, so we know the base name, cyclohexane. Okay. And then we'll go ahead and name the substituents. So yeah, this one's kind of easier. So 1 bromo. And then this one will be 3 chloro. And then this one is 1 methyl. And then you would put them all in alphabetical order for the substituents. Yes. So I'll put this one in the back, methyl, and then this one before this one, and 1 bromo. Does everyone think I did that right? I'm pretty sure. Yes.
Yes.
Yeah, this one, yes, these are my favorite problems. Yeah, so that's that one. Oh, and then let's see. So here you can't do like, there's no cis trans or anything because there's not wedges or dashes or anything like that. This one, oh, whoa, I almost messed that. So this one's a chiral center. So we would have to go ahead and name that, and then
Wouldn't
this one
3
would
be
also
chiral center? Yeah, okay, yeah.
Yeah, okay, cool.
You're not going to be able to define R and S though, because they have to be defined with wedges and
Oh,
dashes.
true. All right, except, well, oh, okay. So like at least one of them would have to be.
So you can't, so you couldn't,
Yeah.
how do you know, you wouldn't know how to like
know, yeah,
prioritize
yeah,
like which is
true.
a dash or wedge bond.
Yeah. Okay, that is also true. So we will not do that. Sounds good. So let's see. No R S, even though I'll just circle the chiral centers anyway. Because cool. Okay. Sounds good. So then we'll just go ahead and go to the next one. Does there have to be? I feel like that one was from earlier. So yeah. Okay. So then the next one. So for numbering, you always want the alkene portion to be first. Even though it wouldn't make any sense if we went that way. But yeah. So 1, 2, 3, 5, 6, 7. So peptine. So yeah. And then we show, well, you don't have to show it's on the one since it is one, or you could write it in. So peptine. Yeah. When it's on the first one, it's kind of optional. So you don't have to do it, but you also can. Okay. And then I'll just name the substituents. So this one's going to be 4, 4 difluoro. Oh, and then someone corrected me last time. How do you spell it? FLURO?
Yeah.
Okay, cool. So that one, and then this one's gonna be 3 iodo. And then you'd put them in alphabetical order. And that's based off of the F and the I and not the di part of it. So this one will be first. This one. Cool. So there's that. And then we do have wedges and dashes for this one. This one's not going to be a chiral center, so it's not RNS, but this one's RNS. Oh, and then this is also, there's a lot. Okay, wait, so no. So first of all, I was looking at this double bond. You can't do easy because these are both hydrogens. So we don't have to look at that one. For this one's easier for me right now. We could do RNS for that one. So we can look at it, and then we have hydrogen in the back, which is going to be our number 4. So it kind of doesn't matter. So I'm just going to leave it out. So yes, so we number it. So this is first priority. This carbon attached to fluorines is going to be second, and then this one's third. So that's this direction, which is clockwise. So this one's R. So there's that one. This one is freaking me out right now.
It can't be
I don't know if
chiral
this-
because it has two,
Yeah,
two fluorides.
yeah. So it's definitely not RNS. Would it be? Well, I guess no. Yeah, I was gonna ask if it would be anything else like cis trans or any of that, just because this is kind of identified, but they're also the same molecule anyway.
Well, they're also
Yeah.
on the same carbon too, so
Yeah.
cis trans would be on different carbons, but it wouldn't work
True
either
that. Yeah.
way.
Okay, cool. So I'll leave that. I'll leave a lot of this actually. Okay, cool. Okay, so yeah, that's that one. Oh, someone corrected me again. Okay, cool. FLUORO. Okay. Okay, thank you. Okay, cool. So that's those ones. That was fun. Now predict the products for the following reactions. So let me see. Okay, so the first one is Lindlar's catalyst. So that's going to be, I'm like looking at my whole list of definitions. I'll actually share this Quizlet letting me copy. It just has all the reactions, so I'll put that in the chat. So yeah, so Lindlar's is alkyne to a cis alkene. So and we'll just go ahead and do it that way. Okay. And then it just keeps it on the end right there, right? Did I draw that right? Can anyone confirm?
I believe so. I mean, it's probably, that's the only way you can draw it, I think.
Yeah, right. Okay, cool. And then HBr is going to be Markovnikov. So the side with more hydrogens gets the hydrogen, so the side would get, do it in this one. This one will get an extra hydrogen. Here, wait, let me just change this. Okay. So we're adding this hydrogen, and then we're also like taking out that one. And then we'll add the Br over here. So then the final product. Okay. Just like that. Can anyone confirm that?
And that's what I got.
Cool. So that's that way. This one. So first is this one, which is like the deprotonating one. So for the first step, we'll just have like the same structure, but we took off the hydrogen at the end. So it's negative. And then CH3Br is just like this. So
I think that actually
I don't
has
know
two
that.
carbons. So what you
Oh
drew.
shoot. True. Oh, okay, true. Oh, okay. So this will be fine. Cool. Yes.
I do that all the time.
I hate those. Yeah. Okay. So quite sure for this one. I just drew it slanted for reasons. It just adds like this one carbon, I guess. Right. 1, 2, 3. Okay. Okay. That's correct, right?
I think I agree with you. That's what I got.
Cool. Okay. So yeah, so that's those ones. This one, provide the missing reagents. Okay, and then we saw this last time, so I'll fix this side. It's supposed to be opposite. Okay. So yes. Okay. So then I guess for this one, actually, I'm not sure how I want to start this one or how I should. Okay.
So they're both alkene reactions. So they're going to be like the hydrohalogenation,
Yeah.
those type of chapter 5
Yes.
problems.
So for the regular one, we could do any halogen. So, oh, okay. So step 1 on probably both sides can be HBr. So that would get you this one. Wow. Okay. First, you'll have the positive charge here. And then does it happen on this side too? It doesn't. Oh, okay. This is a different one. So it's not for this side. I think I'm looking at this other side. Yeah. Okay.
But you would have a carbocation shift if it's
Yeah.
you did it
Yeah.
like that.
Oh, wait. Could I have done it a different way?
Well, I'm trying to see how your way is working, but because if you do a rearrangement, now your OH isn't going to be on that same carbon as your product. It's going to
Wait.
be on a different carbon.
What am I? Well, my OH should be here too, right? Wait, let me. Because if I did a methyl shift, then I'll just have another one coming out of here, which is kind of what's happening anyway. And then this one will be Br.
But that's for the right-hand side, not the left-hand side. Oh, you're doing the right-hand
Yes,
side.
I know.
was
Yeah,
looking at the wrong. I thought you were on the. Okay,
Yes,
because it was zoomed in, so
because
I thought you were on the. Okay,
I
sorry.
did
Yes.
at first, but then I messed it up right from the beginning because that definitely would not be this kind of reaction on this side. That one's going to be like whichever one is anti-Markovnikov with OH. Yeah.
So far, I did it differently than you on the right-hand side, but I think
Oh, okay.
you're still working what you're doing, I think.
Yeah. Okay. Yeah. So that would be my first one, and then from here, and then we could try yours after too, just so we know. Yes. So from here, then you do 2 is going to be this is a 3-degree one, so that's SN1, right?
Yes.
So then if it's SN1, then I'll use like the plus H2O. And then um, okay. That'll just switch this one, and then this one could be considered a wedge, and then this back one. And then, okay, so that's how I chose to do that side. And then can anyone confirm that that one did work, or if it didn't?
I think that worked. I did it differently. I just did a hydration. So I just did like H2SO4, like with
Oh,
the,
frick. So
but
true. Wait,
I mean, that definitely worked. It's just an
Uh-huh.
extra step, but
Yeah.
I totally think that's acceptable.
Does that also give you the like both of them? Then
Yeah, you'd have a carbocation rearrangement. So if it's saying show, and it's also if you show stereo, because you don't know which they're gonna
Oh,
be.
okay, yeah, that's true. Okay, so I'll just put 4. So which one is that? Just hydration, did you say, or is it?
Yeah, H2O and H2SO4. Or I think she said she would accept H3O plus, but
Oh yeah.
that what you're writing right now is more
Oh.
correct or more accurate.
Yes. Okay, cool. Yeah, and let me just kind of show that. Okay. Okay. Yes. So you do that one, either of those for that side. And then for the left side, the one that's anti-Markovnikov for OH. Let me see. So that's these reagents. So it's it's BH3 and THF. And oh, that's one, and this is 2. NaOH and H2O2. So okay. Yeah, so that one will add it in an anti-Markovnikov fashion. So this one will get OH, and this one go and hydrogen. So yeah. How did you know it's anti-Markovnikov? Just because I looked at, so this is our starting one, and this is the one that we ended up with. So this one has 2 hydrogens and 1 other hydrogen. And then, yeah, so I just saw this one added to the side with more hydrogens, which is basically the definition.
What was the second one for the one on the right?
Yeah, so for the right, I went for the difficult way, and then I did
Mhm.
like 2. So I did HBr. I thought it had to be syn addition,
Yeah,
just to get the enantiomers.
Yeah, okay,
But
and then, yeah, what was the second one?
yeah, you could also do H2O and H2SO4.
Oh, okay.
So that, yeah, and then you'll have a shift happen, and yes, you'll
Sweet.
get the same thing. Cool. So that's that one. And then we could go ahead and go to the next one then. Determine the relationship between the compounds below. So let's see. Oh, I think for this one, you could also do R and S. So I definitely just want to try that. So that'll be 1, 2, 3. This one will be the opposite way. 1, 2, 3. So this one is going this way. So this one is R. And then this one's going to be S. This one is going to be 1, 2, 3, 4. So you go this way, but then you reverse the direction. So this way is clockwise. So it's R.
I don't think,
And then, yes.
these
think-
compounds are chiral.
Why not? Wait, I think yes. Because
I
Wait,
think
so-
there's an internal plane of symmetry.
That's what I was thinking.
God, fuck.
I
So
think-
true. I just wanted it to not be hard because we did it yesterday, and then you can also just kind of tell, like if you think about it real hard, that this one is rotated. Which way is it? Frick. This way? Up or
It would
Look at this
rotate
one.
down the one you.
down? Okay.
I
Yes.
think what you were doing, I should have let you finish. It might have still worked, but it wouldn't. I don't like. They might
Yeah.
still be R and S, but they're technically not chiral, so I don't think you would use R and S.
Yeah. That's okay. Yeah, I'll
That
go
I'm
with
not
that.
sure about. That was why I was like, I don't know if you could do
That's
that.
okay. Yeah, I don't know if it would have been right, even if I did get the right answer. So that's fine. Technically would have been, but I don't trust it anymore. So yeah, this one, if you have like a molecular model set, you can see too, it's just this bond is rotated. So yeah. So these ones are the same compound.
Yeah, Natalie, makes a good point that like the centers are chiral, but the compounds achiral. So it might have still worked.
Yeah, I don't know. I don't know what she would have said about that as in the teacher. So I don't know if yeah. Who knows? But that's okay. Cool. Okay. So that's that one. And then for this one, okay, this one is not symmetrical. So the best thing to do would be R and S. So for RNS, for this one, we have 1, 2, 3, and then the hydrogen would be 4. So it's going in this direction is counterclockwise. So this one's S right here, and then this BR. 1, 2, and 3. Okay, so this way is also S. Yes. Okay, so there's that one, and then so we'll do it on the BR again. So this is 1. Oh yeah. Then this is gonna be the hydrogen. 2, 3. And then this hydrogen is gonna make us reverse the direction. So this way is clockwise. So this one is R. This one, 1, 2, 3. 4 is going to be our hydrogen. So the opposite direction of this is this, and that is also R. So enantiomers. But did I do it all right? I kind of went fast. Does everyone agree? Anyone disagree?
I think there's 3 chiral centers, but
Oh, there's one more.
I haven't done all of them, but I did get SS for the ones that you've
Oh,
done.
that's true. Okay.
There is a 3rd chiral center though.
That is, yes. Is it this one? Would it not?
That one you have circled, yeah. It wouldn't be the last
oh yeah,
methyl,
true. Just
but
kidding. Yeah.
yeah.
Okay. Cool. So then one more. I'll do it in a different color. There's so many now. Okay. Also here. So here we have. Wait, this one's gonna give me a stroke. This one is one, or is this one because it's carbon? Yeah, this one is one. Carbon to an oxygen.
I think so.
Okay.
Like,
And then,
yeah,
yeah,
like
two,
how
and
you
then
did the
three.
other one, like the 2 was the one with the BR, even though there's a longer chain on the
Yeah.
other.
Okay, so that's that one. But then we have hydrogen. So this way, except not this way, and it's that way, which is counterclockwise. So also S. Yeah. And then this other one, we'll do 1, 2, 3, and the 4 does not matter right now. This one is clockwise, so it is R. Okay, so then is that what you ended up getting for all of them? Actually, I feel like we ended up getting diastereomers last time.
They should be enantiomers.
Oh, okay.
I think she confirmed that they're enantiomers.
Oh, okay, just kidding. Cool. Well, yeah, so they all have different RNS configurations on the chiral centers. So they are enantiomers. But cool. Probably.
Yeah, and I got all the same RNS. It took me because I didn't do it that way, so
Oh
I
yeah.
was double
Oh,
checking.
okay.
Yeah, it should be
Oh,
all.
did you just like
What I do is just rotate like
Uh-huh.
I flip and rotate the compound. I guess
do you
that's
have it
easy.
built out or you just do it in your head?
I write them out.
Oh, okay, cool.
I can't do things in my head like that.
Yeah. Okay. Yes. Yeah. Cool. Okay. So yeah, that's that one. So for this one, predict if it's SN1, SN2, or no reaction. So I think a good thing to have is SN1. So like what are the properties of SN1 and then what are the ones of SN2? Oh, frick. So when it comes to the structure that they're going to be attaching to, SN2 prefers methyl groups or 1-degree carbons. And then SN1 prefers 3-degree carbons. For the nucleophile, it needs a strong one for SN2 because it's only one step. And then this one doesn't really mind, so a weak one. And then lastly, you could go to the solvents. This one wants a aprotic solvent. And then this one needs a protic solvent. Which means hydrogen bonded to oxygen or hydrogen to nitrogen. So yes. So this one, I just end up doing the carbon is attached to first. So this one's a primary. This one will be secondary. And this one is also secondary. So we know from this one, since it's 1-degree, we know it's going to be SN2. 2-degree could be any of them. Yeah. So then you can look at the solvent that you have. So this one has a hydrogen as the proton. So that's one of the main solvents or reactants of SN1. Yeah, they always have like an extra hydrogen that they can lose. Yeah, so that's that one. And then basically if it's like not a hydrogen that's attached as the proton, then it's like an ionic bond, which means that this is a strong or moderate nucleophile. But it's also just definitely not a SN1 reaction because it's not a hydrogen. So this one is also SN2.
You also have to remember your leaving groups. You need a strong leaving group.
Okay, so then this one, yes, okay, so that is step one. Step one. Good leaving group.
So you would need a strong acid in order to turn the OH into H2O, which would be a good leaving group if the reaction were to occur.
Oh, that is true. Wait.
It's not gonna, it's still no reaction.
Yeah.
I just wanted to say because OH,
Yeah.
how she says OH can turn into H2O and become a good leaving group, but you would need a strong acid for that, and that's not.
Oh, okay. That's the first step. You need a strong acid if it were to happen.
Yeah, like you would have to change OH to H2O with a strong acid first.
Okay. True. Cool. Okay. Okay, yeah. That one does not occur because it's a 4 leaving group. Okay. Do we agree they're both SN2? Yeah. Yes.
Yeah, she confirmed also the others are SN2.
Okay. There's that one. This one, they have 2 vials, compound A and B. They're both pure. So they're either the same compound, enantiomers or diastereomers. So state the physical properties they should analyze to determine the relationship. Yeah, so just what properties can you look at? Oh, uh-oh. Okay. So this was at the end of chapter 6. And then what are some of them, if anyone remembers them? Oh, okay.
It's a silly question. Like, why would she ask us this?
Yeah, this is in fact silly. But also just to remember, so diastereomers, they're gonna have different physical properties. And then both of these have the same physical properties, enantiomers or compounds that are the same. Okay, so some of them were like, it was like boiling point, or was it melting point?
I think both.
Okay, and then what's like another one?
Let me grab my notes.
Yeah, you could also go to the.
So there's boiling point, melting point, density is the same.
Oh yeah.
Solubility. The only thing that differs for enantiomers is the optical activity. So like their rotation and plane of polarized light. I don't know how that's said. So it's either like plus or minus. So they'll have the same number, but it's plus or minus, and that's what makes them different. And diastereomers will have different
everything.
optical rotations or whatever. Yeah.
Cool. Okay, yeah. So those are some of the things that are different. And then I'll just show it on here. So that everyone knows what I'm talking about. Yeah, right here. So these ones are enantiomers, so they have all the same information: density, solubility, melting point. Boiling point isn't on there, but that's fine. Surely that also. And then this one's the diastereomer of them. And it's all different. Yes. This one. Okay. So that's that one. Okay, cool. So then we could do 7, predict the major products. So yeah, we could do that.
Also, guys, pay attention to the question. If it says indicate stereochemistry, it's basically saying like show the enantiomer if there's one.
Hmm.
So like
Hmm.
there's some problems that you would assume you don't have to show it for, like when you do chapter 5 reactions, but if always show the enantiomer if it says show stereochemistry, just so you know.
Okay. Cool. So for this first one, it's a alkane, first of all. So this one's not going to be like hydration or anything like that. This one is one of the major solvents for SN1. Even though that doesn't even matter, because SN1 is just replace it with the OHs. It's going to end up being OH, and then it'll lose a proton. So yeah, so it's going to be like the same thing. Yes.
You have to remember though, well, so that's a,
Mhm.
so for what kind of alkyl halides work for SN1 reactions?
For SN1, water is one of them.
Well, like, no, I mean like what
Oh,
alkyl
alpha
halide,
halides.
like is it primary,
Oh,
tertiary?
Freaking frick. Chelsea. Chelsea. Yeah.
Help,
Keep me
yeah.
on my toes. I know. 1 degree. I'm testing everyone else. Okay. So that is true. So it's 1 degree. So it can, yeah, only be SN2. Oh, which is going to get the same product, right? It doesn't really matter that it's.
But for SN2, what kind
Well,
of nucleophile do you need?
Yeah, you need a strong one. So, oh, no reaction is allowed. Okay.
Yes, no
Okay.
reaction.
Cool. So yes, so this one it's 1 degree, so it tells us it's SN2, weak nucleophile, so it doesn't happen.
So Alma, in case if we didn't explain it enough, the alkyl halide, so the carbon attached to the chlorine is the carbon we pay attention to in the alkyl halide. So it's a primary carbon. So those can only do SN2 reactions. But for SN2 reactions, which she listed, we need a strong nucleophile. So it essentially has to have like a negative formal charge. So since water is a weak nucleophile and technically only works for SN1 reactions, there would be no reaction. And Natalie, I'm pretty sure she confirmed it was no reaction with me. Because it,
Yeah.
because because for the same reason I had just explained, I don't know that a SN2 reaction would actually go through with H2O. Okay, cool.
Okay, so that's that one. This one, let me check. Because for this one, okay, we talked about it last time. The excess makes me feel like it does like the alkyne to alkane, but does it or no?
I believe it does. The excess.
Oh, okay, it does both.
Yeah, like there's a plethora of H2, so
Yeah.
it's gonna take all the bonds down.
Okay, cool. yes, so this means like add hydrogen basically instead of like all of the double bonds. So it keeps like the same kind of structure, but it's just all an alkane. So yes, that one. Okay, for this one, let's see. So iodine is a good leaving group, and then our okay, so it's attached to a 3-degree one, so it's going to be SN1, and then yeah, so that's that. It's going to be SN1, so I'll just take this. Oh my god, okay. So this one, this is a chiral center. Sorry, and then we'll have our group right there. So it'll have both enantiomers, but I'll go ahead and finish this. And then it'll end up deprotonating, so we won't have that. So we'll have OC10O and CH3. Let's drop it. Okay, cool. That, oh fuck. Okay, sorry, it's kind of ugly. That one, good with everyone. Cool. So that's that one. And then, okay,
Or you could also
Ye-
just write plus enantiomer if you want it. If you need to
Okay,
say
yeah,
you could just put plus enantiomer. In case y'all are Russian.
yes. Okay. Okay, cool. So that's that one. And then for this one, now I think I saw it on the homework too, because we weren't sure if this like is a reaction.
She
I'm
said
pretty sure
it is,
right?
yeah, because
Okay, cool.
technically they both have their charges, yeah, so it'll
Yeah.
do the reaction.
Cool. So this one's gonna be, well, okay, let's see. So this is gonna be a substitution reaction. This is a primary carbon, so it's SN2. Yeah. And then, yes, this is a good leading group. That's cool. So it's just going to be like the same thing with the iodine replacing the bromine. Right.
Yes, just, yeah, sorry.
Oh no, I
Looking at it to see if there was any, I was checking to see if there's any chiral centers and if there, but no.
Oh, good question. Okay, but we don't have to indicate or anything. Yeah, cool.
You would only need it to be indicated if you're naming the compound.
Yeah,
But it's
but
not a chiral center, so.
yeah,
'cause there's
if,
2 hydrogens.
well, yeah, would you even be able to, because if it were a chiral center, I don't know, because it's a
You would
line
just,
structure, so it wouldn't
if
really
it
matter.
was
at that
chiral
point.
center, so if you had like a extra carbon.
Yeah.
Like if it was
I drew a little methyl for you.
Yeah, like if you had
Okay, cool.
something like that and it was chiral, then you would just show, because you're showing enantiomers, so you're gonna show
Oh,
both options. So you would just,
yeah.
whichever you choose to show the wedge and dash and then plus enantiomer.
Oh, okay. You would just give it a wedge and a dash.
Yeah. Yeah, because
Oh,
you're showing both
okay.
compound, like both
Mhm.
possible compounds, so.
True. Okay, cool. Cool. Okay. So then this next one is, so like looking at like the quiz that I have, it's alkyne to a transalkene. So you like the same structure. Okay. I always end up doing these weird. This is fine though. Okay. No, it's weird again. That's fine. Okay. Something like that ish. Right. I mean, that's so ugly. We can just 1, 2, 3, 4, 5, 6, 7. Okay, technically correct, right?
Yeah, something like that. I mean, you could just bend the like
Yeah,
diagonal.
a little more.
Same thing.
Yes. Cool. Yeah, I don't know why I'm so bad at drawing them. Okay, cool. All right. So I think we're all good on that one, unless anyone has any questions. Okay. Cool. So 8, fill in the missing starting material by drawing, yeah, whatever the compound. So I'm pretty sure this is a strong nucleophile, but I'm kind of a little scared to label it as such. What do you think?
Well, it has a negative formal charge, so
Charge,
it has
so
to be,
yeah.
it would be a strong one. The only ones that I
Oh,
about is
yeah.
like the homework problems that had the nitrogen, but she even
Oh,
said that
yeah.
those are kind of weird. Like they're a bit of an exception. They're moderate nucleophiles that still work for SN2 reactions. So,
Mhm.
but as long as it has a negative formal charge, I mean that's how she's showing us to assume that it's a strong nucleophile. So
Yeah. Okay, cool. Cool. Yeah, not even that it matters, I don't think. So yeah, it'll just be the same structure with a good leaving group right there, right?
your dash and wedge bond will matter.
Wait. Oh, true. Okay, good.
SN2 have transition states, so you have to remember like how it's attacking, from what side is it attacking.
Yeah. Okay. Yeah. So SN2. I'll write a note for that too.
And she said that you could use, like you put Cl as the alkyl halide. I used Br. She says that any of those are fine as long as they're good leading groups.
Good. Okay. So yeah, SN2. What? Frick. I thought there was a better way to say it.
Inversion of stereochemistry.
Yeah, that one. Okay. Okay. Cool. Okay. Yes, that is a good note that I will need to make for myself too. Cool. So that's that one. Okay. So then 9. So this one wants you to show the whole mechanism. So yeah, we can go ahead and try and do that. So I'll just redraw. Well, this will be for a bit too. Okay. Something like that. So I would go HBr. So I think I'm just going off of what I remember. I think so. I think that the double bond grabs a hydrogen and this one goes off by itself. Yes, that is correct. So then we'll have a hydrogen on this side, and then we'll have a carbocation on this side. I'll actually make that all one color because then there's going to be a methyl shift. So, or sorry, a hydride shift. So to indicate this correctly, is it just like that? Just right there?
Yeah, it's just to the carbon,
cool.
I believe.
So cool. Okay. And then I'm just not even going to show it at that point. And then the positive charge. And then I'll go ahead and draw. We still have the BR. And this time it's gonna attack right here or wherever. Yeah. Okay. Sorry, I didn't even look at. Oh, okay, yeah, same thing. Forgot it gave us the end project. BR. Yes. So those are all the steps. Can I zoom out on this one? Yes. Okay. Was that good for everyone? I trust. Okay. Okay, so then we could go to 10. Provide the mechanism for the reaction. Yeah, okay. So this one is going to be a substitution reaction. Yeah, because it's an alkane. So that's good. Leaving group SN1 because weak nucleophile. And then, oh yeah, and then also this is 3rd degree carbon. So yes. And then let's see. For drawing out the mechanism, I might struggle a little bit. I'll definitely need my notes. Okay. So, okay. So step 1 for this reaction. Is going to be the leaving group leaves. I'll just do that. Let me see. Do you think that we would need to show the BR in the flask at all or anything? Or
Oh,
it's-
what? I'm
it's-
sorry.
The bromine, do you think we would have to show it like plus BR at all anymore? But we
No.
don't use it anymore.
No,
Yeah.
she says that she
Okay.
didn't. I'm pretty sure in lecture she said she didn't care about that.
Cool.
Once
Okay.
it's gone, it's
Oh
gone.
yeah. Okay. So first leaving group leaves. And then second nucleophilic attack. So we have that one, and then we have, let me see, H2O. So this one will, whoops, will attack the carbon. Oh shit. Okay. Then we'll have H2O here also. But it needs to do deprotonation. Oh no. Okay. Okay. Yeah, so this one's going to be positively charged. So we'll have to do deprotonation, and then you do that with the rest of the solvent in the flask. So this one. Oh, okay, this one goes up to this hydrogen, and then these electrons grab, or well, I should send them. Oh, okay, it grabs this hydrogen. So then I'll go this way, I guess. You're left with and OH right here. And then this last step with deprotonation. Okay. Cool. Is that one good for everyone? Okay, so then we could go on to 11, which is the last one, which is awesome. So provide the reagents necessary to transform it into this product. Let me see. I'm not sure if I know where to start with this one. Some sort of substitution reaction.
So first you need to do an alkene reaction, but
Mhm.
you're gonna need a leaving group also to get the OCH3 attached, right?
Okay, yeah, true. So, okay. Yeah. Okay, so I guess this is throwing me off, like the extra one.
It's so count your carbon chain, count how many carbons you have in your starting material.
3. Or well, I guess you would go do this one, but yeah, 3. Oh, or just in general 4.
Yeah, just
Oh.
however many, because that's basically it just moved a position or not position, but
It'll make
it's the same 2 carbons at the end.
okay. Okay. Oh wait. Okay, yeah. I think that makes sense to me. Okay, so just like a HBr kind of one, or anything like that.
Yeah, HBr, HCl, or HI are your alkene reactions for hydrohalogenation.
Okay, this makes sense again. Cool. Yes. So yeah, we just added our BR group coming out of here. Yes. So that's our first step. And then second step, this is a third degree one. So it's going to be SN1. So it'll be this just with like a hydrogen in front, basically. So I'll say SN1 HOCH3. Cool. Wow, that was the whole first one. Great work, everyone. All right, I guess I wasn't answering these. True. Okay. Anyone have any questions on like anything from this first one? Cool.
Des, are you also going to post your notes apart from the video?
Yeah.
Okay, thank you.
For the last question, when it says show your work, does that count as
Oh.
work?
No, probably not. Sorry, I didn't. read
Yeah,
that.
she said like when
Okay.
it says show your work or show some work, like literally anything could be counted as work.
Okay, so
It
this
doesn't
would
seem
be
like she's super particular about it, as long as you show something, like you just write SN1 3 prime carbon.
okay.
Or
Yeah, maybe
yeah,
that wasn't important.
that's kind of how
Yeah.
she stated it. So I don't know.
I mean, that's definitely my work for the second part. It's not too much.
Okay, thank you.
Cool. Cool. Okay, that's that one. We could go ahead and go to the next one. Hopefully we could speed run it. Oh, actually, I don't even think I was able to get to the end of this one. Okay. So naming is like pretty easy. We could also like skip any if you guys want to like try and be fast or anything like that. I don't know if anyone's interested. Okay, so I'll just kind of do it fast. So nonane, and then it's on the second carbon. So 2 nonane or nonene. And then we have 4 dibromo. Yeah. Oh, okay. And then we also have this one. I forgot what this was last time too. Methyl, ethyl, and then propyl. Yes. Was it in a different color? Nope. Okay. Okay. Okay, so then you'd put this in alphabetical order. So this one here. Okay. Okay. So that's all the substituents and stuff, and then we have to do easy or RNS and all that. So this one, that's supposed to be an H. Okay, so this is trans or E. So we'll go trans. And then, let's see. Okay, and then, oh, that one's not, this is not a chiral center. This is a chiral center. Yes, so wait, 1, 2, 3, 1, 2, 3. No, it's not, right?
I don't think so.
Okay,
No.
cool. All right, so that one's not a chiral center because 2 of them are like the same. So yeah, so it's just trans 4 dibromo 6 propyl 2 nonane. Nonene, yes. Okay. That's that one.
I think for well, trans would work. I think she might prefer E though. I think
really?
I think she would still mark it correct, but
Yeah.
only
Yeah,
because
because I mean like the same thing. What is
they do mean the
trans?
same thing, but I think the trans you would need like your wedge and or no, I don't know.
Yeah, it could be
Sure, it's
like
fine. Sure, it's
either of
fine.
them. Yeah. but E is only for double bonds. But yeah, trans could be also for wedges and dashes. Cool. So that's that one. So to determine if it's going to do a rearrangement. Yes. Oh, so show the mechanism also. So it's going to do a hydride shift. I'll just show it on this side. So hydrogen, and then it just moves over right here. Then you'll have this hydrogen here, which you don't really have to show. And then your positive charges on that one instead. Oh, okay. And then indicate the type, and it was hydride. So that's that one. And then let me see. I think that question is old. Yes, I am gonna post this. I'll post the notes in the Discord, and then I'll also post the recording. Okay, so determine if these are R or S. So yes. So that's our chiral center, and then it goes based off of atomic number. So the highest atomic number is bromine. It's 35. And then it would be fluorine, which is 9. And then oxygen. And then this is our fourth one. And it's already in the back, so we could just do the direction that 1, 2, and 3 are already going. So that is counterclockwise. So it's S. Nope, wait, that's regular clockwise, right? I'm very bad with my clockwise and counterclockwise. Yes, okay. Okay, so it's that one. And this one, this is our chiral center. This is 4, 1, 2, 3, because this one has a double bond. So that means since it's wedged, it's going to be the opposite way than what it's going. So it's this way, which is clockwise. So also R. Cool. So that's that one. And then this one is the same as that other one, compound A and B. These are the boiling points of them. So what's the relationship? They have different boiling points, so they're diastereomers. And then briefly explain why, because they have, I'll just say like totally different physical properties. Let's see. Yeah, and then I don't know, she probably won't even ask this, but yeah, if it was the same compound or enantiomers, they'd have the same properties. So that's that one. This one, decide, yeah, their relationship. So these two, this is dashed, or sorry, wedged, and this is wedged. And then these ones are also dashed. And then if we're numbering, we number through the double bonds of 1, 2, 3, 4. 1, 2, 3, 4. So these are the same compound. We just like rotate it a little bit. So it's D. And then for this other one, I forgot what the other way she said we could do it is. But first I'll do, so for this one I would do RNS because that one's the easiest for me. So this one is 1, 2, 3, 4. And then this one is 1, 2, 3, 4. So this one it's gonna go in the opposite direction of that, so that is counterclockwise. That's S. And then this one, you do, well, I always do like the human projection of it. So this one's like in the back, and then this one is straight down, CH, whatever it is. Oh, but better it's 2. And then if I'm looking at it from this side, then the OH is on this side. And then the CH3 is on this side. Okay. So,
Sorry, Desiree,
I lie?
I think you might have done the first one wrong.
This first, or wait, this first one?
Well, because or the other one, I'm sorry.
Oh, okay.
Or that's the one you're doing right
This
now.
one. The one I
Oh.
was doing? Okay.
I'm so
yeah, that's
sorry. Just ignore me. Sorry,
worries.
guys. Sorry.
Not wrong, you think?
No, go ahead. Keep going.
Okay.
S is
Okay,
the
yeah.
other one. Yeah. I thought you
One,
had
yeah.
put S for the first one.
Oh, okay, yeah, no. Cool. Okay, so yeah, and then this one is R. So they are different, and they only have one chiral center. So they're enantiomers, right?
I also got the same thing.
Okay, yeah. Yes. Okay. So then we could go to 6, SN1 or SN2 reactions. And the first thing I'm going to do is look at these. So that one's a good leaving group. This one's not a leaving group. So this one's no reaction immediately. The other 2 are. So that's cool. Then we can look at this to see what it's attached to. This is 3rd degree carbon, which is an SN1 trait. So yeah, that one's SN1. This one is just a primary carbon. So that is SN2 trait. So yeah, those ones I have a lot of practice with. Okay, I think that one's good. Also you can tell because this is like a stronger nucleophile because it's like ionic. And then this one, that one could do either, right? H2O.
I think it can only do SN1.
Okay. Okay. Cool. Yeah. SN1 solvent. And then there were a bunch that were listed, so those are very helpful for me. Kind of a lot to list out, so I guess I won't right now. But anything with like, yeah, 2 H's and no other like positively charged thing is going to be SN1. Okay, what's that one? Okay, this one, provide the missing reagents. So this one, we notice that, let's see. Okay, I'll go this way first. So we already have a good leaving group here. So we're just going to replace it with OH. So yeah, this is, that's a 2nd degree. So it could be either. But yeah, we see that this one changed. Oh, tell me what it is again. Inversion of stereochemistry. Yes. And yeah, that's what happens in SN2. So then the reagent could be like anything like ionic bond with any OH or yeah, anything like that. That's that one. This one has 2 products. So that's SN1. Yeah. So then an SN1 reactant that'll make this is going to be H2O because it'll end up being deprotonated and then you just end up with OH. That's that one. And then we could just go to 8. So predict the major product and indicate stereochemistry.
I just realized that this whole section is worth 22 points.
Oh my shit. Yeah, she would. That's so crazy. Oh my god. Yeah. I think this one might be better because I've practiced a lot now, hopefully. Okay. So this one's just an alkene to alkane. And then it's Markovnikov addition kind of thing. So the hydrogen will add to, here, wait, I'll just write it over on this side. So the hydrogen will add to this side. I guess I'll do it in one. And then the Cl will add to the other side. So yeah, we'll just end up with, oh, okay. Cl. Looks slightly odd. Yeah, let's do it straight down. No. Okay,
Are there any carbocation rearrangements?
thanks, Queen. Surely there are. Surely there are. Oh my shit. Okay, I have to make a note of that. That's so awful. And okay, so yes, so first we'll deprotonate this, and then the positive charge will be here first, and then whatever hydrogens, and then we do a hydride shift. So we'll switch that over here, and we'll just end up with the positive charge here. So then our chlorine will attach right there.
This is also what I meant by when it says indicate stereochemistry, because she wants us to show the enantiomers of these. So like you would have the chlorine and the methyl dash and wedged and then plus enantiomer.
Okay.
So I think we all
Okay. So
didn't think that because of the whole syn addition thing. like
yeah.
how hydroboration has syn addition, but that just means they're added to the same side. So when it says show stereochemistry, if there's like a, basically if there's a chiral center, you just have to pay attention if there's a chiral center and then show an enantiomer.
Okay. Cool. Yeah, because I didn't even know that it formed both of them when we were doing this chapter. I don't know if it was said, but yeah. Okay.
No, I just think that that's something we should kind of like apply now.
Oh yeah.
Is it because of chapter 7?
For this one, this will turn it into a trans alkene. So okay. Okay. So that's it for that one. This one. That reaction gives you OH and H in anti-Markovnikov way, right?
Yes, it's a hydroboration reaction.
Okay, cool. Oh, and in addition, okay. 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 So that means the hydrogen will add to the side with less hydrogen. So we'll have a hydrogen here. And we'll also have the OH over here. Or we'll have the OH on this one. And it's in addition, so you do have to show the stereochemistry. Okay, so then if we're showing, should we show just a, yeah, that would be safe to just show the hydrogen as a dash. And then so this ethyl will be wedge.
Yeah, just that first part would be dashed.
Yeah. Or yeah. that.
I always get them mixed up when I'm saying
They're
them.
just words, whatever. Okay. So okay. And then yeah, okay, whatever. Something like that. Oh, plus an andromer. Yes. That's that one. Nearly done. Okay. NH2, and then so whenever it's these ones, I draw them out. So this one, yes, this one looks like this. BR. And then this first one is just going to deprotonate it. So there is an invisible hydrogen at the end. So it'll just yeah, look like that for the first step. But then here, let's see. I'll leave that actually. So that'll just add right here. I'll do straighten that. Oh wait, you don't keep the BR, right?
No, the BR left. It's an alkyl halide, so the BR group left, basically.
Okay. Cool. Okay. So yes, let me 1, 2, 3, 4, 5, 6, 7. So 6, 7, 1, 2, 3, 4, 5. Okay, and then this last one, this one just adds hydrogens instead of the double bonds, so it's just the same structure but an alkane. Cool, so that's that one. So then number 9, draw the missing starting materials. So BR2, it just adds to each side of a double bond. So it'll just be like, well, I think that technically it would be in the structure it was in the first place. So just
So halogenation is anti-addition.
was it? Okay, here, wait, let me see. I'll just put that there for now. But
Yeah. Yeah.
oh wait, yeah. Okay. Really?
Yeah.
Okay, cool.
Because if you rotate the product, that's basically
Oh,
what that's your anti-addition of the
Wait,
bromine. No,
you're saying if
the
I drew it like
no,
that?
the product. Sorry, if you rotate the product, because you can't rotate the double bond.
Oh, okay, yeah. Sure.
Technically.
Oh, okay, yeah. I see. I see. Oh, okay. Yeah.
So if you rotate the
Technically is what it
product,
is.
like if you either one,
Yeah. Or something. Yeah, it would be in the same conformation.
it'll be the same as your starting material.
Yeah.
And it'll show that it's anti-addition. So one will be wedged and one will be dashed.
Mhm. Okay. Oh, I didn't even pick up on that though. Wait, let me find it then really quick. Yeah, anti-addition. Okay.
What always helps me is like rotating the compound around. It's
Yeah.
kind of hard to see it like that,
I
but
know.
if you get it down, it's actually pretty simple.
Mhm. Mhm. Okay, cool. Yes, that's that one. Go to 10, provide the mechanism for the reaction. Okay, so look at this. This is 2 degrees, and this is a good leaving group, so that's fine. Yeah, and then we just look at this one. This is like an ionic bond, so there's gonna be SN2. Oh, okay, and then we also see that this inverted inversion stereo. What? Wait, stereo. Yeah, cool. So that, and then provide the mechanism for it. Let's see. Mm, Well, I think I could just do it all in here. So it all happens at once. So this one gets kicked off, and then oh frick. Okay, I'll redraw that. Mhm. Okay. Yeah, and then it's backside attack. Which is probably going to be important when you draw the arrow. Just because, yeah, we know it gets inverted. So yeah, that's the whole mechanism, right? Just do it right there.
Yeah.
Cool.
You can show the carbocation there's no rearrangement, sorry, but if you wanted to
Yeah.
show the intermediate, I meant, sorry.
Oh yeah.
But I
Yeah,
don't
you
know
could do like
that, I don't
yeah,
know.
that like
It might be
dash.
necessary. I don't know if it's the
Oh,
mechanism.
that's a good question. I'm not sure if it is.
Yeah,
I
I'm not
think
sure either.
I would think no, because it's ugly. Hmm.
Well,
I'll
definitely if there is a rearrangement, you would show it, but I don't know
for
if
these ones
there isn't one.
because it's SN2, so
Oh, no,
I'm
you're
pretty
right.
sure
So
yeah.
there is no carbocation. Good job.
Yes. Yay. The student becomes a teacher. Okay. Cool. So next one. Provide the mechanism for this one. So this one is, we can see it's anti addition. So this is like halogenation. Yeah. So okay. Provide, oh wait, ew, this is a gross one. Okay, hold on. Let's see. Hmm. Does anyone know off the top of their head how to show this? I know she went over it in officers, but simply cannot. Okay, I think the first thing that happens is that this double bond grabs this chlorine.
Yeah, draw the lone pairs in. That's important. She's gonna want to see the lone pairs. It's gonna be like a double attack for the first.
Yeah. Oh, okay, wait, I think I remember. So this one attacks the chlorine, but then this
a lone
one.
pair. Yeah, it's gonna whatever.
Okay.
And then she says you just pick a carbon that chlorine is gonna that lone pair on that chlorine is gonna form a bond with.
Okay. So then, does it matter if I do a wedge or a dash, or would it be either right now?
Yeah.
Wait, hold on.
As long as they're anti.
Oh, okay. They're anti even just when it's the first one.
No. So what okay, so no, your carbons
Yeah.
are what, yeah. So your carbons are those have to be the same. Either it
Oh,
doesn't
okay.
matter if they're wedged or dashed as long as they're the same.
Okay. Okay. And then we'll have this other one. Oops. Okay. So then I assume like this one just breaks off onto itself and then one of these. Right? Something like that.
Yeah, so the wedge bond, like how you have it, is gonna create a lone pair on the chlorine. And then that chlorine, you would have to attack the other carbon, I believe,
Wait,
if you're, because that's,
I'm breaking this one. So this one's free, but this one will have, well, I guess it'll not have 4, but it'll have, so if I'm breaking this bond, then I'll be left with that one with the chlorine, right?
I don't know, I guess, because how she did it in the
Mhm.
office hour today, she has like how you have it, that first arrow from that wedge bond to that chlorine,
Mhm.
but she has the chlorine from that, yeah, to that carbon.
Okay.
So now
I feel like that might be true. Let
confused
me,
now,
oh wait,
because that
yeah.
doesn't make sense.
Let's
I think it
yeah.
would be the other, because if
Yeah,
that bond is breaking, so it,
yeah, it does make sense, not that way.
yeah, but that's how she has
Okay,
it there also.
well, this one
no?
is,
Oh,
yeah,
okay.
from the notes, and that one's the way I did it.
Okay, yes, your
I
way
think that's
definitely
fine.
makes sense.
Yeah, so
I
we'll
think
go with
maybe
this
she
one.
just got
Maybe, yeah. Okay, cool. Okay. Oh, or actually, I think that this might specifically mean that they're anti-addition, possibly.
So like,
Yeah.
so that
Um,
chlorine already on the compound will stay wedged with the bottom carbon. And
yeah.
then the new chlorine will be, it did a backside attack, so.
Yeah, I know. That's why I drew it to the back specifically, just in case that means something. Okay. Hmm. Cool. So that's, yes, that kind of thing. Awesome. Yes, the last one. Okay, so the necessary reagent for this one. Let's see. So I know we also did this one. 1, 2, 3, 4. 1, 2, 3, 4. Yeah. Okay, same amount. I'm thinking a trans alkene, or it probably doesn't matter which one, right?
I don't think it would matter just
Mm.
because it's a terminal
Mhm.
alkyne, so it's gonna come out the same anyway.
Okay, cool. Let's see. So for, yeah, Na, oh, whoops. I think it's like this. Yeah.
I'm pretty sure she said in the office hour today that she would accept
Yeah.
NaH3 or the H2 and Lindler's catalyst for the first step.
True. So then from there we have okay. Then that'll get us this, and then
I
our
think you
step.
have an extra carbon.
Oh shit. True that. Okay. Yes. Okay. So we have that one. Step 2. The OH is adding in a Markov-Nikov fashion. So that's gonna be H2O and H2SO4. Okay. Yeah. And that is all of the exam prep. Does anyone want to go over any of these ones again? Just a lot of rules. Cool. Awesome meeting, guys.